So welcome to the first talk of the semester in our seminar series of the ICS. So it's my great pleasure to introduce the first speaker of 2022, John Regan. So John obtained his PhD at the University of Cambridge in 2008, working with Martin Ennelt on numerical simulations of the IGM. And then he literally moved around the world as a software engineer, as a lecturer, then as a postdoc, before going back to Ireland, first as a Marie Curie in 2016, I think, and now he's a Royal Society Fellow at Maynooth University. So John is an expert of the early universe. He's worked on many state-of-the-art simulations of a high-redshift universe. And today he's going to talk about the emergence of massive black holes in our universe.
Thanks, Pedro. That's true. What Pedro said, I did after my PhD, I took a break from research actually. My wife is a diplomat, so we had kind of a two-body problem, and I was following her around for a few years, which was really cool actually. We got to live in Zambia and then in Finland, which was good. So actually, if any of the PhD students or postdocs want to talk to me about that, I'd be more than happy to share my experience, because I had an unconventional career path. So, it can be useful. Also, this is where I now am. This is Maynooth University in Ireland. It was, it still is today the biggest seminary in Ireland. So this is where all the priests train actually. And this is like the nice part. It's like where I am. It's not as old. And so I think what happened was actually, so the priests were really good at certain things, not everything obviously, but they actually taught physics there very early, like from the 1920s onwards. And then over the years, of course, that expanded, and in, I think it was 97, the Maynooth University was incorporated what's this is St. Patrick's College. Okay, so you can walk through here, it's really cool actually, where we have lunch in here, and you go in here and there's a long hall, it's got all the pictures of all the graduate priests, and you can see like the evolution. Like if you start like 50 years ago, there's like a huge, you know, they can't even fit in the frame, and now it's like 3 people. So it's very interesting to watch it. But anyways, that's the history. What I will talk about, oh no, I'll have to come closer, is, oh, is that not working now? Oh, there, hopefully that will work from now on. But anyways, that's the history talk. What I'll talk about today is most of my research on early universe black hole physics. So, and mostly the formation pathways of black holes in the early universe. So, just to motivate the talk, the origin of central supermassive black holes is unknown. So I think a lot of people probably know that. That, you know, for example, even the massive black hole at the center of our own Milky Way, we have no idea what the progenitor of that black hole was, whether it was a small black hole or under solar masses that grew. Like started life with a more massive black hole. There's a number of pathways potentially leading to a supermassive black hole, but we've little or no empirical evidence. We've no observations to guide us really. Every now and again, we get some tentative evidence from a high redshift observation, but it tends to disappear as quickly because they're very difficult to interpret. So we don't really have any clues at the moment. What we do have are simulations. And the simulations are very good at this because in some ways the early universe is quite well defined. We can start our simulations at least from a consistent viewpoint and try and evolve them forward and try and see if they at least give us what we expect, even if it's not what we can yet observe. We have JWST, of course, coming soon. So that potentially could provide some very interesting clues, but it's unlikely to be definitive, simply because it won't have that. You know, won't be able to look back far enough. And then we have gravitational wave measurements in the future. So a good plot to always start with, I think, in this is just to see where we're at. This is a EM sigma relationship from only a couple of years ago from Vivian Baldessari, where she added in these points here. Okay, so this is the mass of the black hole here on the y-axis, and this is the velocity dispersion on the x-axis, which gives some handle on basically the mass of the galaxy, if you like, so, or the potential well at least. And you can see it's well defined up here. This has been well defined for a long time, where massive galaxies follow this very linear relationship. And then what we have down here is is people like Jenny Green or Vivian herself or Mar Macuza in Spain were really trying to populate this part of the diagram. Okay, it's very difficult actually to get a handle on the mass of the black holes down here, because these are ones now that are around 10 to the 5 solar masses, and the of course the velocity dispersion here is around 30 kilometers per second, and a black hole around there only has a sphere of influence of about half a parsec. So it's very, very small. So if you're trying to get dynamics for that, it's very, very difficult. So it's a great achievement to even push it at this level. Of course, pushing it down further then becomes complex, because now if you push down another order of magnitude, let's say you get a black hole down here, then you're at 10,000 solar masses, and it may not be central. Okay, it's not necessarily in the middle. So then this relationship can easily become skewed. We haven't got there yet, but it's certainly going to become more difficult to interpret. But of course, this field and this realization started over 40 years ago. Martin Rees gave a kind of what certainly has become, in hindsight, a seminal lecture in Oxford. I think it was the Huxley lecture, is the name of it. And he produced this plot. Okay, because at the time, he and his contemporaries worried about the discovery of quasars, because quasars were at this stage known to be creating supermassive black holes, but they were also being discovered at relatively high redshifts, at 3 and 4 at the time. And even then, the issue of, well, how could such massive objects originate so early in the universe? How could they get there? And Martin had drawn out this diagram, and I would argue that we still work on large parts of this diagram today. And only a few of them, if any, have been resolved. Like I think this was a very good path he drew out. Like a supermassive star is certainly still a leading pathway to a massive black hole. Like Lionel Hammerley and Tyrone was still working on that a huge amount and have made great progress. And it looks to me like it certainly represents a very strong pathway to a massive black hole. Other ones, as I'll talk about, the where is it? One black hole grows spectacularly by accretion. Difficult, right? And I'll talk about that. But it's still possible, but difficult. And there's a range of reasons for that. But anyways, just to give you a little bit of insight, Martin voluntary then. 30 years later, and a few of these kind of like plays on Martin's diagram have been over the years. I had one in 2007, but Marta absurded me with a better one, and also I'll have to absurd her again soon with an even better one. But this is what she had. So there, and this is kind of where the field is at. This is kind of breaking it down now. If you concentrate first of all just at the top here, this is your first star in a first galaxy. And the idea here is that we expect the first stars to be top heavy, not as top heavy as maybe we did a couple of decades ago with the original simulations, but 100 solar masses wouldn't be unreasonable. And then you would hope you get a black hole of something similar, and that collapses. So you have 100 solar mass black hole you start with. And these are what are coined the light seeds. Okay, and that could be a very nice place to start with. And in some ways, it's the most obvious as well. And if you're kind of new to the field and you don't believe in anything exotic at all, and you're kind of risk averse, that's where you would definitely put your money. Okay, and I'll talk about that as I go along. The next two are more exotic then, especially the middle one here, where we have a supermassive star of about up to a million solar masses, I would say. This one was kind of, so this encompasses both the supermassive stars that was right in the center of Martin's plot, but also these quasi-stars that Martha and Mitch Begelman would have worked on around this time. And that's kind of where this diagram originates from. So something around a million solar masses, or up to a million solar masses. And then we have something similar. Actually, I actually think these two are kind of almost the same, because you could easily imagine how one interacts with the other one. This is where we have a dense stellar cluster, and the dense stellar cluster either core collapses and the stars collide, or else they, in a slightly different mechanism, they turn into black holes and the black holes collide and merge, and we get something similar. But either way, you get something of about 1,000 solar masses. So these two are the heavy seeds, so somewhere between 1,000 and 1,000,000, and then at the top we have the light seeds. But how can we differentiate the pathways becomes the answer, or the question, rather. So we have these light seeds between one potential pathway, and then we have the heavy seeds. One way we could do it is back to Vivian's plot. So back to the M sigma relationship. If you saw a plume, if you saw that plot to a plateau at some sort of a 10 to the 4 solar masses or 10 to the 5 solar masses, then that would be a clue to what the original seed mass was. But it's difficult to interpret. And that would be observationally. The other way is that we use simulations, and that's probably our best mechanism at the moment, and obviously needs to be complemented by future simulations. So just to give an overview of what happens here with simulations, or diagrams here of this one is illustrious. People probably know this is the Eagle, and this one is the Renaissance simulations. Large volume simulations are constrained to have ad hoc procedures for black hole formation. So they drop black holes into the center of massive halos. Okay, that's possibly okay. It's probably wrong, but it has advantages, and it also has, it's necessary. There isn't any other way to do that. And as large-scale simulations have become more sophisticated, so has the mechanism for dropping black holes into galaxies. But you're still fundamentally dropping a black hole into a galaxy. What you don't do, and there's a reason, can't, they have no mechanism to identify the formation pathways. So there's no way to know how that black hole originated or what pathway it took along, of course. And it, of course, also assumes a 100% occupation fraction. And that in fairness, is probably okay. What you would like to do is, of course, have small volume, high resolution simulations to do this job for you. But unfortunately, they have the opposite problem in some ways. They get stuck at high redshift. And as well, they struggle to evolve to lower redshift. So they kind of can do some of the early work, but then they can't join the dots fully. And they struggle to model the formation. Nonetheless, the project that I was involved with, at least in the post-processing, was something called the Renaissance simulations. So the Renaissance was out of the Dark Ages. Dark Ages being, prior to star formation. What these were very high resolution simulations, the ENSO simulation. What initially is a 40 megaparsec box, okay, centered on a massive cluster, I think a few times 10 to the 10 at a redshift of 6, and 3 regions were cut out or zoomed in on, if you like. A rare peak region, which is an overdensity, a normal region, mean density, and a void region, underdensity. And those 3 regions then were re-simulated at much higher resolution. So the mass resolution was about 10 to the 4 solar masses, for those who are interested, and the spatial resolution was about 20 parsecs. So parsec level resolution, or a few times that. The goal of the simulations was to understand the birth of the first galaxies. So it was predominantly a galaxy simulation suite. It captured, and the idea was to capture population 3 and population 2 star formation. That was kind of the main goal of the simulation. And that it did that very, very well. The disadvantages inherent to the simulation, of course, was limited evolution. So this says Z8 up here at the top, but that some way a lie. It was only the void region that got to Z8. The normal region got to 11.8, and the rare peak only to 15. Okay, so you really are trapped at high redshift. The reason they all got to different redshifts, of course, is the different level of structure involved in each region. So by the end of the simulation, each region had the same level of structure, but at a different time or a different redshift. Okay, so you have those three different ages, if you like, of the simulation. There was no black hole prescription either, which was, I suppose, like that wasn't. It was just because the simulations didn't have that in mind. These were just predominantly a galaxy formation simulation, a galaxy birth of the first galaxy. So they were more interested in following POP3 and population 2. That's almost completely true, and there's a little caveat in there that I'll talk about in a minute. This might play. I'm not sure. Let's find out. But the sound, I don't think will come through the speakers. I think will come. Let's see.
The Renaissance astrophysical simulations are the largest and most complex calculations of their type. Time-evolving visualizations give insight into dynamics that are impossible to understand from quantitative analysis alone. Only through simulation can we study this era. Early galaxies burst with new stars and flood the universe with light. The most massive stars explode in supernovae, spreading heavier elements, called metals, to their surroundings, promoting future star formation. Supernova explosions also drive star-forming gas out of their host galaxies, locally limiting star formation. The universe rapidly evolves as galaxies assemble. Over 15 million computational hours on the Blue Water supercomputer modeled gas, stars, dark matter, and radiation, producing a host of physical variables. Cool, neutral hydrogen gas traces the dark matter that forms filaments and halos. The most massive stars produce tremendous amounts of ultraviolet light, ionizing the surrounding gas. The resulting clouds of ionized hydrogen reveal galaxies where stars had recently formed. Ionization, as well as shockwaves from supernova explosions, heat the gas. Heavy elements from supernovae enable gas clouds to cool, collapse, and form the next generation of stars. The combined physical variables show the anatomy and structure of the modeled early universe. We're now approaching an early galaxy only 1,000th the mass of our Milky Way. Though beyond the reach of present telescopes, the James Webb Space Telescope will detect these tiny distant galaxies. With its observations, scientists will be able to test if these large-scale computational models are capturing the essence of galaxy formation in the early universe.
Yeah, so that was the Renaissance simulations. They were, like I said, run about 6 or 7 years ago now. So one of the things that it neatly allowed us to do is actually look at the different pathways and see which ones work as massive black hole seeds and which ones are less attractive, let's say. I'm not going to say they don't work. It's hard to be absolutely definitive in these things, but certainly less attractive. So if we go back to our talk about our light seeds, just for 2 or 3 slides, just minutes. These are, again, just to remind you, these are your 100 solar mass stars, and then therefore your 100 solar mass black hole. And you might think, well, we'll have lots of those. Surely one of them will be our breakthrough black hole, and will grow and seed a supermassive black hole. And that seems very attractive. So if we look at simulations, some of probably the best ones are the state of the art, maybe were conducted. If you go back and look at literature, there's like a peak there in the middle of the last decade. Athena Stacey and Shingo Harada really drove this field a lot. And the best kind of like the state of the art simulations were showing black hole mass up to about, or star masses, black hole mass up to about 100 solar masses, and with characteristic masses below that. But we'll see a tail to higher mass. But 100 solar masses or a couple of 100 solar masses seems absolutely reasonable as is a mass for these most massive black holes. Okay, so could these be seeds? Could these be the seeds for the most massive ones? So what we actually did was we looked in Renaissance then, because what Renaissance did was it took an IMF of what is expected to be the mass of the first stars and had that distribution of masses. And then I said it didn't have a black hole prescription. That's pretty much true. What actually happened at the end point of these stars is they just turned into passive particles. They were like tracer particles or like small dark matter particles, if you like. And they didn't accrete or have any feedback or anything like that, but they did stay in the simulation. And they just essentially traced the hydrodynamics at that point, or the potential as well, the gravity. So we, in post-processing, what we did about 4 years ago is we looked at these black holes. And it was, I can't remember now, but it was 20,000 black holes or something like that. So it was a pretty good sample. And we looked at their growth rates. And if you look here, so let's see the average growth rate. Don't worry about the different colors here. These are just the rare peak, normal, and void. They all look the same statistically, because again, they have the same structure, same level of structure at the end. And the average growth rate is somewhere between 10 to the minus 20 and 10 to the minus 10 solar masses per year. So effectively zero. These things don't grow. The maximum growth rate, so here on this plot is, okay, well, let's, the average doesn't look great. Let's look at the best optimistic scenario. Let's look at each black hole and see what was its maximum growth rate at any point in the simulation. And it's it averages around 10 to the minus 10 Eddington, of the Eddington rate, with a small tail to something around Eddington growth. Okay, so almost zero. And the ones that we looked at, like the top 10 that I remember as well, and they only had that for one single time step, ever. None of them grew any more than that. So, like this is the best case scenario.
Just a question.
Yeah.
You're treating them as seeds?
Yes, post-processing.
In post-processing?
Yeah, using the body oil accretion rate.
Okay, so that was my question. So it's just the body oil accretion.
Yeah, and you just see, like, you can basically see the black hole is in a clump of gas. You're like, okay, well, if it had been accreted, what would it have accreted to? Okay, and I can't remember then, but I think at the end of it, we found that the most growth of any of the black holes, and I remember there's about 20,000 of them, was approximately 10% of its mass. So it went from 100 solar masses to 110 solar masses. Great stuff, right? So these things do not grow, at least not easily. Okay, that was our conclusion from running them. Now you could argue, and I think that's a fair point, these simulations didn't run very far. Absolutely, that's a restriction. Okay, it could be that they get into bigger galaxies and then they start to grow, possibly. Okay, but they didn't grow in any of the modeling we did, or any of the simulations that we ran. So that was that. Well, the reason they didn't grow was this. So we took one of the galaxies. Here, I think it was 80, if I remember correctly, black holes in this galaxy. We looked at what did these black holes do in this galaxy, and all they did was just wander around, because they're very, very small and they just follow the potential. And in this plot, what I'm showing here is coloring each black hole by the distance it is from the nearest clump. And the clump here are these dark green bits. So the darker the green value, the more clumpy it is. So it's actually, so that's a good description, but it's actually the accretability. So if it gets into one of these dark clumps, it has a high probability of having reasonably high accretion. The trouble is they never get into these clumps. For one thing, the clumps disappear from photoionization, or else they just form stars as well. Okay, because obviously a dense clump of gas, which would be ideal for accreting, is also ideal for forming stars. So they should turn into stars before the black holes ever reach it. And then finally, Britain who made these plots, he's very, very, very good at making very pretty plots. And what he was showing here on the top right was how far the average black hole is from a clump at any point in the simulation. And on average, a black hole is a kiloparsec away from the clump. Okay, even if it was a parsec away, that'd still be too far, but it's a kiloparsec away. So it's really not a good, it's a very difficult problem. These small black holes just don't find themselves at the center of a dense globe, simply because, they're too small. It's just not easy. So how can we form heavy seeds? So if the light seed model isn't attractive, I'm not saying it doesn't work, but it's not attractive. How can we form heavy seeds? How does that pathway work? We need a few ingredients here on the left. We need a large Jeans mass. So we need a lot of gas that's gravitationally unstable that's going to form a large object. We probably want to suppress early population 3-star formation. They're kind of mutually exclusive at some level, because if you're forming population 3 stars, you're probably not forming massive seeds. So we want to suppress that. Low metallicity, because high metallicity would induce fragmentation. High infall rates, because we want it to grow quickly, and suppress maybe H2 formation. Maybe, okay, because that would drive fragmentation and population 3-star formation. So maybe you need that. I'm not sure all of these are needed. Certainly some of them are needed. What mechanisms are there for it? Lyman-Werner radiation, that disassociates molecular hydrogen. So if you have a lot of Lyman-Werner radiation, that's just below the ionization threshold of hydrogen, so it's about 11 electron volts, 12. That will disassociate molecular hydrogen. So that at least was seen as being the leading contender. Streaming velocities is the offset between dark matter and gas. If you get a large offset, you can get that in certain regions of the universe. It's not everywhere, but you can get tails of that. And that can mean that the gas can't settle in galaxies as quickly. And then you can get a larger galaxy before star formation kicks in. People have done a lot of work on that, and that looks promising as well as a mechanism, or rapid halo assembly as well. That's not a new idea either. It's been around for at least 20 years. And that's where a galaxy grows very quickly. And that growth of the galaxy, the rapid growth of the galaxy, heats the gas and prevents star formation. So not terribly dissimilar to Lucio, what you did 10 years ago. I think the principle is similar. Okay. Just maybe the scales can be different. That's all. Okay. So how do we do that? So again, back to the Renaissance simulations. Funny, when we came to making these slides, are almost like looking back in hindsight, we did things completely backwards when we did this. It's funny the way science works. But anyways, so what we should have done is like the way I'm doing it now, it's kind of like, a logical sense. We didn't do that. But anyways, so this is the rarity region, okay? And what we did is we saw, okay, you have all these galaxies. So let's look at them and see if if any of them have no stars. So like, if you like a dark galaxy, okay? It's big, massive. It's at the atomic cooling threshold or across that. So the gas is rapidly cooling, but it's not forming stars. Why is that? Okay, it's because that would be an ideal region to form a massive black hole seed or massive stars at the very least. And we found, I think it was 78 of them. I've labeled them here or circled them. Now, this one is kind of, this is kind of like there's a bit of poetic license here. This is, of course, this snapshot is at one redshift, but these circles appeared at all different redshifts. But I'm circling the halos that were in just for visual purposes. But over the course of the simulation, now it's only up to redshift 15, so it wasn't terribly long. But over that course of time, we found 78 of these halos. Then, using our time machine, we went back 2 years and wrote a paper on this. This is not the way we should have done it in hindsight. But we looked at two of the halos, actually only at one snapshot at redshift of 15, probably because it's the easiest thing to do. And we looked at two of these halos in detail and re-simulated them actually at high resolution. And we found that we didn't actually understand first, actually. When we did this first, it was funny. I was actually at the first stars meeting in Heidelberg. And I was going through John Weiss and I were analyzing the data we had because I'm curious to look at these halos. And we found loads of them. And John, I remember looking at the raw data, John showed it to me, and we assumed, I suppose, initially that Lyman-Werner radiation was the cause of this, that it was dissociating molecular hydrogen and not allowing stars to form. And he showed it to me, and I was like, "Oh, those numbers don't even make sense. They're way off." Because I was used to looking at the raw data, and I was like, "Oh, understanding code units." I was like, "They're way off. They don't make sense at all." And sure enough, when we looked at it, the Lyman-Werner radiation values in the community are 1,000 J21. If you're not familiar with that, don't worry, just keep 1,000 in your head. And what we found is values of 4 were impacting these halos. So we're like, there's no way this is Lyman-Werner radiation. Something else is preventing star formation. And so we looked at this in quite a lot of detail. We took 2 halos. One is the most massive one, and you can see the bias kicking in. We also looked at the most irradiated halo as well, the one that got hit by the most Lyman-Werner radiation. That was still 4J21 or 5J21, something like that. You can see the bias then. Here it is. Here's the values of the J21. But actually what we found was not that. It was actually rapid assembly or dynamical heating that I've labeled here. If a halo grows really quickly, you can see that this is the mass here against age. So it's DMDT or DMDZ if you like. What you're reading, you're seeing very rapid assembly here. You can see the galaxy can drop in mass as well. That's because there's some tidal stripping. But you see rapid assembly, and this is where star formation then occurs. It's above the atomic cooling limit, which is when neutral hydrogen will cool the gas. But the rapid assembly or the dynamical heating caused by the rapid assembly is literally dependent on the growth rate of the halo. Okay, so if you've got a rapidly growing halo, you get a lot of dynamical heating. If you get a lot of dynamical heating, then that's in opposition to cooling by molecular hydrogen. Okay, so if it grows fast enough, then you just simply can't grow. Okay, that's just physics. Okay, it just can't happen. And then that's almost independent of the amount of molecular hydrogen you have, because that's not a limit. It can't just be, oodles and oodles of molecular hydrogen. That's well defined how much you have there. So even if you kind of have the maximum molecular hydrogen that you would expect in these halos, if the growth is strong enough, you just won't cool. Okay? And that's exactly what we found. And we found that in these two halos that we looked at in detail, and we resimulated. It's a very high resolution, like 10 to the minus 4 parsecs. So very high resolution. And really didn't see a huge amount of fragmentation. And very nice. So I guess hammer layout, I think Rod's here, right? He's gone on to better places now.
No, he's Geneva.
Okay.
He's often here.
Oh yeah, okay. Okay, sorry. That's right, yeah. And so he'd be very happy to saw this, because the critical rate for star formation is around a few times 10 to the minus 2 solar masses per year. So that's a lot of gas flowing in. But we see that all the way down to about 1,000 solar masses enclosed. So that's really far in. That's, if you compare here to where that is, that's around less than a parsec. So very far into the halo, very high accretion rates. So ideal for forming very massive stars. I'm not saying that this won't fragment. You do see a bit of that. So that's why I think, when if you remember back to that plot I had, where 2 heavy seed scenarios were in there, kind of coupled, I think, that you might get some fragmentation, but then those things could easily merge again. So you'll just get very massive stars, basically. I'm not saying it'll be one very massive star. I don't actually think that's true, but at least not in most cases, but you will get very massive stars forming. And the gas doesn't cool down very much. It does cool initially, and then that rapid gas inflow heats up the gas again. And the molecular hydrogen fractions are actually quite high, okay, and still not forming stars. Okay, great. Okay, so yeah, so in those ones we didn't have a prescription for star formation, because we were just interested in okay, does the result hold under very high resolution? And then what we did was, okay, well, let's see, does the result hold under very high resolution with star position? Okay. So again, very high resolution simulations, very zoomed in onto these target halos, spatial resolutions of 10 to the minus 3 parsecs, mass resolutions of about 100 solar masses in dark matter, because you don't want any shot noise. And we included a prescription for massive star formation or supermassive star formation, which can track when we have rapid infall. So once you have mass infall onto some sync particle of above a few times 10 to the minus 2 solar masses a year, then you can form a supermassive star. Okay, and so we looked at that and see. So I think we can move this. Here, I'll play it a few times because it's kind of it's goes really quickly, but it's also like watching the fire. It's very addictive. So you can see so you can see all the stars forming. It's really chaotic as well. That's one of the other things you come out of these small galaxies from. So the most massive one is always in orange or yellow, if you like. It's 2,000 solar masses. You can see when these little disks collide, you often get very massive stars, more like a triggered star formation.
These stars, black hole.
Stars.
We can have these stars at these masses.
Yeah, looks like it. So yes, yeah. So this is actually at the end then. This is the most massive one we found at the end. I only ran it until I would expect supernova explosions to start going off, obviously other layer complexity. And then it was the amount of inefficient supercomputer time I was burning at this point was getting hair raising. So we ran it again for about 2 megayears after the first star formed. The most massive star we had at this point was 6,000 solar mass, and you can see then there's a tail down 4,000, 2,000. So this is one of the halos. We also had a control simulation though, where we took we didn't do anything. We just took one of the smaller halos to make sure our prescriptions were working. And that one, with the exact same star formation prescription, formed a normal population tree halo with maximum mass of a few hundred solar masses, and a characteristic mass of 50 solar masses. The other one though, which we zoomed in on, was this weird halo, of course, particularly weird, but one that had this rapid assembly. You can see what it does to the stellar masses. It really pushes them up by 1, if not 2 orders of magnitude, just because you're delaying star formation, the default goes soaring, and the rapid inflow as well. And the most massive star was 6 times solar mass, with a peak somewhere around 1,000.
Can I ask another question?
Sure.
So does this mean that you didn't find efficient Lagrange thing to prevent? So did you find them, or?
So yes, like it is necessary. It does appear to be necessary. You need to have a small level of Lyman-Burner radiation. No Lyman-Burner radiation is actually what happened here. There was nothing, and this one just collapsed. Okay, something. So, but that's something is like 4 or 5, 10, something around that order. It's not 1,000. Okay. Now I'm not saying that the 1,001 will work too, but you'll need that if you have the rapid assembly. And I think if I don't know if Zoltan is on this call or not, I don't want to say anything because he is. But he probably would argue that the favored situation is still a very strong Lyman-Burner radiation field, because that will get you to even higher masses and allows the star to grow in even bigger halos. But what's absolutely true is the rapid assembly is going to be more ubiquitous and more common. Okay, so it's difficult to know where we're at the moment, which one is going to see. Yeah, anyways, I can talk more about that at the end. So that's more of a longer description or longer discussion. So that's pretty much where we're at with those simulations. So I have a couple of minutes left, right? Yeah, like 5 or something. So now we have another simulation suite in the works. Where we're doing something a little bit similar, but with full black hole prescriptions and full supermassive star prescriptions, and we targeted a very massive halo, so something around 6 by 10 to the 11, so order of magnitude larger than what we did in Renaissance. So we're purposely looking at an incredibly biased region, okay? Because not because what I'm trying to say is it's not a disadvantage, I don't think, because obviously you're going to look at a very biased region, but more because of the advantages it gives you. It brings out the physics. It doesn't, if you look in a rare region, you're like, oh, well, you should look in rare regions in normal regions, because that's what we generally see. I'm like, that is true, absolutely. But the problem with that is that it won't bring out the physics of what we're looking for as easily. If you look in the rare regions, what you'll see is this rapid assembly happening all the time in tandem with the Lyman-Burner radiation and with metal pollution. And you can kind of start to disentangle. Okay, they're all tangled together, but at least you see the physics. And we only saw rapid assembly because we looked in the rare peak region. Well, if we didn't have that rare peak region, we'd never have seen this. So this is absolutely the place to look. What we're doing at the moment is we've identified this. We've identified 3 clusters within this rare peak region. This region here is 10 megaparsecs moving. The clusters we're going to resimulate, or are resimulating, albeit incredibly slowly, are about 2 megaparsecs. These should actually be 2 megaparsecs moving, and we're running those ones down as far as we can run them. So these ones have spatial resolutions of about 1/10 of a parsec and mass resolutions of about 1,000 solar masses. So that's about as good as ENSO can do at the moment, the current version of ENSO. We just can't do it better. We're just limited by that. Some really early preliminary results. I'm kind of embarrassed to even show these. So we have a lot of galaxies so far, but actually have thrown these simulations away. I know it's really super preliminary and obsolete now. You can see central infall rates. These ones here, this is the infall rate within 5 parsecs. So we have some very, very massive halos. Very high infall rate halos already. A lot of them, of course, are not, and you expect that. But we do have a handful of them which show this real rapid assembly. The halo growth though is very, very high for a lot of halos, because you're in such a clustered region, they're growing like wildfire, because they're completely always hammering into each other. There's always mergers happening. So you get this, you get a lot of dynamic releasing occurring. It hasn't really got to the point where star formation is kicked off yet. But what we can look at is we can see already the telltale sign of what the dynamical heating does. In the colored halos here, you just focus on the colored ones for a second. That's the predicted cooling rate from molecular hydrogen. So if there wasn't any dynamical heating, this is what the cooling rate would be. But that's not what we find. These are the actual measured cooling rates from the cooling algorithm in ENSO or Grackle, for anybody who knows. They're much higher. So these things aren't cooling, but they should. Okay, and that's because they're being dynamically heated. And you can translate this into a Jeans mass. You can translate that into a stellar mass, and then you get something of an order or two higher. That's exactly what we see. Okay, and so that's basically where we're at the moment. So those simulations are perplexing me as they keep dropping out. So issues to focus on. It's going to put up conclusions, but actually I think it's funner to put up issues to focus on. The number densities of massive black holes is still an open question. I haven't talked about that at all in this talk. That was on purpose. So that is something our group are working on. So like Mark Digestra worked on this and others over the years. But like, you know, if you look at the literature and you look at the number densities that are predicted, they vary by orders of magnitude. So this is definitely something we need to look at, because if you want to make a prediction for LISA, this is right in that equation, right in there. And like, so if we don't know that by orders of magnitude, we have straight away got a serious problem. The dynamics inside early galaxies. So you can see in that movie that I was showing you with those stars, that thing is just, you know, crazy. You know, it's going to be really hard to do dynamics. And Martha as well, and her group have worked on that. And Hugo Pfister had some lovely papers on that, where he looked at, you know, the black holes have to get to a mass of about 10 to the 5 before they settle into these halos. So it's interesting to look at the dynamics inside there. Some gravitational wave foregrounds as well. It's something I think is still probably not worked on very much. I could be wrong. By that I mean like the weak lensing and how that is going to impact gravitational waves detections. And then the statistics, this kind of feeds back into the number densities as well a little bit. So that's kind of what I guess I'm trying to do with those simulations at the moment, is trying to see, okay, well, what are the ones, which black holes form from rapid assembly, which ones are forming from Lyman-Werner radiation, which ones are coming from a light seed. So, and where does that all end up? Is it 1% in light seed? Is it 0%? Is it 10%? You know, are heavy seeds 0%? Are they 100%? People don't even know that. You know, there's a big open question. And again, that feeds back in the number densities. And then how we interpret these things electromagnetically and with gravitational waves. So obviously we have JWST flying, you know, blown, or, you know, orbiting at the moment. And it'll be interesting to see what that brings out. I think it's absolutely obvious that it's going to bring out results that we don't expect. And that's, of course, what we want. If people might remember back to CR7 a few years ago, you know, we had that interpretation. People didn't know how to interpret it. It's likely JWST will show us something as well. And it's also, I had a paper with Tyrone Woods there about a year ago, where he was able to take those simulations of those supermassive stars and show that because those stars are really, really red, they can show up with JWST, and we might be able to identify them. Like, that's, you know, difficult for sure, we don't know, but if JWST sees very red galaxies, that can indicate supermassive star formation because they're very, very red. They're not blue, okay, like population 3 stars. So they look different. But again, you know, it's a distant universe, so it'd be hard. Okay, I got to leave it there because I do have conclusions, but you've already heard me talk long enough, so I think that's enough. Yeah, thanks. You're telling him his job.
No, because it's of the bank and we didn't see the
That's true. So I have a question. So you just mentioned briefly super-Eddington accretion.
Yes. Yeah.
So my question is, do you think it's not needed because you wouldn't even help, or do you think it's not happening?
I don't know if we know enough to answer that. It'll definitely help. Be great. But what we found, so I did some work with this Martha a few years ago, and what we found that, and these were 3D simulations, and other people in 2D have found slightly different results, so it's hard to know. But we found that the super-Eddington feedback shut off the accretion. Okay, so that was a problem. especially the jets just blast everything back. And so what you get is this, but it's not that it stops the accretion actually. It's more like it's episodic. So you get a spike of superheating accretion, really strong feedback, no accretion. Okay, and then the gas falls back in. And then you get a spike in superheating accretion again, and get the same thing happening. And if you average that out, it turns out that is a fraction of Eddington. Okay, so it doesn't help hugely then, right? Like it's like, well, that's no good almost. You know, you'd nearly be as well off hitting that optimal Eddington zone, and that would be faster. But I think really more work on that. I suppose it's always more work on that, right? But yeah, the initial results didn't look great. I didn't feel the need to progress it after that. But that wasn't all that. Didn't look like it was going anywhere very quickly. But that doesn't mean that's definitive or anything. Yeah, I don't know. But the other thing is, the other problem with that is that if you have, and that was for a fairly massive black hole. I think it was 10 to the 5 or a few times 10 to the 5. Anything smaller than that is going to move around the potential so much that it's going to be really hard. Like you'd have to get awfully lucky. Like you'd have to get superheating, then quickly move to another dense clump and do superheating again, quickly move to the other one. And I think Alessandro Luffy did something like that. They showed quite good growth, but everyone was pinging around, I think.
Yeah, but the question is how lucky. I mean, the numbers are. You don't need to explain too many.
Yeah, that's true.
So maybe you can be lucky.
Yeah, absolutely. And that's kind of, I think, where I'm kind of putting down the statistics part.
Yeah.
Like they will only find that through like, I don't think you're going to do that by taking one halo and, even if you idealize it and then be like, okay, let's, work here. You need to take a huge selection of them and then be like, okay, let's see what the field looks like now. And like you have this rare one over here and it didn't work, but there's a rare one over here where it did work. And now you're like, okay, actually 1 in a million times this doesn't work. And maybe that is enough actually. 1 in a million is actually enough. 1 in a billion is actually enough. Right. So that's kind of what I mean with statistics. Do you think that's a much better way to look at the field at the moment than, well, I suppose, I'm biased because I'm more interested in looking at the statistics at the moment of like, let's take a huge selection of halos and see what the pathways look like. Now, looking at 1 or 2 halos is still very useful as well, but you can't do both. Okay, that's kind of what I mean.
I guess this also falls under the statistics bullet point. If you don't need such strong Lyman-Werner radiation to have this direct collapse happen, and you just need this massive growth or rapid infall, does that make it too easy?
No, I don't think so. No, absolutely not. And that's kind of what I think it's your name. Oral. I stopped the conversation with Laura because they're almost two different questions. One is you're thinking about the quasars at Z6, but they're a very rare object. There's multiple quasars below that, or multiple massive black holes below that threshold. Okay, so we still need a mechanism to form lots and lots of massive black holes. Now you might need the Lyman-Werner radiation or the strong Lyman-Werner field to form the most massive quasars. That might still be true, but we still need a mechanism to form all the other massive black holes as well. Okay, so they're almost two different questions, or they're the same question if you frame it in a different way. But so, like one of them is the peak distribution, one of them is more one of them is the Taylor distribution, and one of them is everything else. Right.
Connected to that, actually, there's also the role of metallicity. We didn't talk much about it. So,
as
you go to the larger halos, of course, you expect more metal enrichment at some point.
Yeah.
So the more rapidly growing ones might be also the more metal enrichment. Statistics.
Yes.
I don't know if you looked at them.
We did. I was thinking about this in the way this morning, and I was like, I don't have any slides on that. But no, we did. So we actually did that too, and I can show you those plots in the afternoon. We looked at the metal halos at all levels of metal enrichment and see how their growth rates were as well. But of course, growth doesn't care about metallicity. So we just saw the most rapidly growing halos, of course, were metal enriched. Absolutely, because it's not like, well, I won't grow quickly because I'm metal enriched. Doesn't care about that at all. So no, that's absolutely true. So it's absolutely likely that what you'll get is very massive black holes in already metal enriched halos. Because why not?
Yes, no, that's one thing that I always push for in our scenario, which is consistent with
Yeah. And actually, that was also the backwards way we did science as well. I mean by us, because I think in that paper we were like, oh, well, we focused as well on the pristine halos and we discounted the metal ones initially. And then we looked at this and we're like, oh God, we're idiots. Right? That was a complete bias for us to put in. The metal enriched ones are metal poor ones. They don't need to be totally metal enriched. Absolutely grow very quickly. And they could be really great sites for this because supermassive star formation does depend on metallicity, but it's not that strong a dependence. So they could easily be, candidates as well. So then, and this back to kind of your question, then you're just going to get this huge, plethora of black holes. And it shouldn't really depend that strongly on metallicity. No, a little bit, because if it's too metal enriched, then supermassive stars can't form because of chemical reaction network. But up to a certain point, no problem.
Can I just ask a question again for this regarding these supermassive stars?
Yeah.
So I think it's very interesting. So am I right in assuming that they essentially disappear very quickly again and then sort of form a mini quasar or something?
Yeah, yes, like their lifetimes are short, around a mega year. And then at that point, it's a direct collapse into a black hole. Yeah, there's no supernova explosion or anything like that.
And you can, so you can say something. So you said, if I heard correctly, you said they are primarily forming in these rare peak regions because they need very massive growth.
Yes.
So this would say something about the power spectrum of the distribution. I'm interested in that because of, these things might be observed over 21 centimeter.
Yeah, perhaps. Yeah, absolutely. They should be predominantly in these clustered regions, like you said, or rare peak regions, over dense regions, because you want this rapid growth, and you won't get a rapid growth, of course, in an underdense region. So absolutely, I don't know what the 21 centimeter signal would be like. That would be interesting to look at. I don't know enough about that.
Yeah, it would affect the temperature of the gas.
Sure.
Via the black holes.
But would that be easy to extract out the overdense regions, or you'll just see a peak? Is it?
Well, you see a peak in the global signal, but you can look at the power spectrum and then see if it's in everywhere or
just at small scales.
Yeah.
Okay. Yeah. That would be interesting.
But you have looked into, because you said in the beginning that at redshift 8 the void is essentially similarly clustered than at redshift 15 the peak.
Yes, that's true. But that's true. Now you don't see the same halo growth though. I don't have a plot of it now, but I'm just trying to think of the plot in my head. So when we looked at those, those halos, those dark galaxies, if you like, the ones that didn't form stars, we found, I think, 78 of them. Let's say it was 75 in the rare peak region, 3 in the normal, and none in the void. So they are really, focused on the rare peak regions. They don't form in the underdense regions.
I have a question related to the topic before. It was interesting. It's something that I never thought about, because you need a mechanism that makes the high redshift quasars very quickly up to billion solar masses, but also a mechanism that makes all of the other supermassive black holes.
Sure.
And I was wondering if you could expand a little bit, if this supermassive star scenario, essentially how likely it is that it can explain both, or if there are some fundamental differences between normal supermassive black holes and these high redshift quasars.
Yeah, I think that's this, right? At some level, okay? And so what I would say is that, so let's just take this one. I think you could easily argue that to get to the quasar, you want a star out here. Like one that's 10 to the 5 solar masses. Yeah. And if these ones are populating really the rest, this is more like the normal. Okay. And then if we really want to push it, it's not clear actually, because we don't have the statistics on it yet. We don't have, don't have that. And not clear that if you wanted to get to the quasars, you need a truly supermassive star, which would be the canonical value for that is 100,000 solar masses or 1 million solar masses or somewhere in between. And that they're the ones that populate the Z6 quasars. I don't know. And that maybe these ones do everything else. These are the smaller, massive black holes that are, 10 to the 7 or 6 solar masses at a redshift of 6, so a million solar masses or 10 million solar masses. I don't know the answer to that question yet. Nobody does, I don't think. So we're still trying to figure it out because this was one halo.
Yeah.
Okay, it was selected to be a really nice halo in a really good region. It's exactly what we were, after for a long time, but it's one. We need thousands of these. And then you start to see the distribution and the growth and how does this, what happens when this halo merges with another one of a similar mass, and those black holes merge, and then it merges with another one. Where do we end up by Z6? Because this is at Z, I don't know if this is 16 or 15 or something. So it's still got quite a lot of, it's still got, quite a long time there, 500 mega years to go until Z7 or something, well less, but like 300. And so what happens then as this one merges and grows, where do they all end up? Might not be. These might be enough as a starting point. I don't know. I don't know if we'll ever get to the 100,000 or billion solar mass supermassive star. And I also am not sure it's necessary, which is good because I think they'd be damn hard to form. You need really specific conditions. Now it could be, at least monolithic. It could be that you get a couple of them merging after a while and then do end up at some point with this really truly supermassive star. But I wouldn't like to hang my hat on that one. This one looks much nicer and more natural to me, okay, as a starting point.
This one being lots of smaller ones.
10,000 solar masses.
Yeah.
With a lot of fragmentation going on, because fragmentation is very hard to avoid. So this one looks more natural to me. One that's 100,000 solar masses, and that's the only one you can form. And if you have any fragmentation, that doesn't make sense. I'm like, okay, that's quite the criteria there. And I'm not sure we can do that. Not sure it makes sense.
Is there a way to estimate how often they would merge? Because you mentioned that you have around 80 of them.
So that would be kind of back to dynamics. It wouldn't be a huge, no, they shouldn't merge that frequently actually, unless there's something, because it's the potential, almost isn't a potential well in these early galaxies. They're so small. Like if you were to plot the potential, it would be like that. So these things are just bouncing around. So no, they probably wouldn't core collapse until the galaxy either gets larger, much larger, and that'll be through a merger. And that's where you get they'll have turned into black holes by then, of course. So, yeah.
Lots of sources for these.
Yeah.
For one last
Just
question.
really quick, can you say at what redshift you would expect these galaxies to then have a deeper potential well?
Well, that depends on the over density of the region. Like by a redshift of 10, though, definitely. I think, yeah.
So you could just delay the mergers because there isn't.
Oh, yeah, if you're asking at what point maybe they should start to be more easily detectable, or the signal becomes high enough so that there's enough of them. I'd say by a redshift of 10, you should be absolutely fine. Especially in these regions. So these ones are growing so rapid that there are massive galaxies at this point. Yeah, absolutely. 12 more. Yeah. Which is good as well good and bad for trying to run these simulations. You might think, you only have to run simulation to 12. God, you can do that surely, But they're so dense. Yeah, there's so much going on in them. It's absolutely killer. Yeah.
Right. So let's thank John again.